Okay, class, we're back. All right, now we're going into additional formulas of importance in blood vessels. All right, we now want to talk on flow. Okay? Flow equals change in pressure over resistance. Change in pressure over resistance. Okay. This comes from something called Ohm's law. Change in pressure is the pressure from one end to another end divided by the resistance. Change in pressure over. So something would move from a higher pressure to a lower pressure. Something would move from a higher pressure to a lower pressure. Okay. Let's think about it. Higher pressure to lower pressure. Okay. So if we look at it moving from a higher pressure to a lower pressure, then let's think on this. Let me enlarge this a little bit so we can all see it. Okay. If it's moving from a higher pressure to a lower pressure, what could impede it? That means hold it back. Some form of resistance. Okay? So think of it. How much flow it would be is how big would the pressure difference be from the higher to the lower. If the pressure from the high side to the low side is big, you would push harder. It would move faster. You would push harder. But then what would be an opposing force? The resistance, the hold back. So flow equals change in pressure, delta means over resistance. This comes from something some of you may have heard of called Ohm's law. So then it would equal to, so then to say it another way, flow would equal to let's say pressure 1 minus pressure 2. And see, to go in the forward direction, that would mean pressure 1 would have to be higher than pressure 2. So there would be a number up here. Otherwise, it would be a negative number. So what are we saying? That P1 must be greater than P2. Okay? But P1 minus P2 needs to be divided by the holdback force, which is resistance. Okay? Hopefully that you kind of see I'm going with that. All right. Now, when it comes to gases and liquids, there are two flow descriptors. One is called rate of flow and the other is called velocity of flow. One is called rate of flow and the other is called velocity of flow. We want to discuss that. All right. One is called rate of flow and the other is called velocity of flow. Okay, so we go to this one. Rate of flow versus velocity of flow. The rate of flow is how much per some unit volume. For example, how much, milliliters per minute. Milliliters per minute. The velocity of flow, so this is the rate of flow. Here's the rate of flow. It's bolded. Is how much per some unit time. How much per some unit time. How much per some unit time. The velocity of flow is how much per some unit time per cross-sectional area. How much per some unit time plus over cross-sectional area. So that would then be, an example would be, in this case, okay, for example, let's say, for example, it could be milliliters per minute per cross-sectional area. Milliliters per minute. Just change this. You know how the computer likes to change stuff. Milliliters per minute per cross-sectional area. Okay, so let's go further. Let's think of it this way to help you. Let's compare a solid object to a continuous substance like gases or liquids. A solid object has a discrete structure like a car. It has a definite beginning and a definite end. When gases and liquids are flowing, they have kind of a fuzzy beginning and a fuzzy end. Okay, so I'm going to say a solid object versus more of a continuous. Continuous would be the gas or liquid. So in my example, I'm going to say a car traveling at 25 miles per hour. What do you know about that? It says how much distance, the area, that would be the miles, and the time, which would be the hour, and how many, one car. So it's telling everything. Now, let's use this. A liquid flows at 25 milliliters per minute. Let's see what that says. It says how much, 25 mils, how much time, a minute, but it has no area. They both look similar, but it has no area. This is what we would consider to be rate of flow. Rate of flow. Let's go back. Rate of flow. How much per some unit time, for example, milliliters per minute. Now, if I said the liquid flows at 25 milliliters per minute per meter squared, that meter squared would be, let's say, an area. That would be the velocity of flow, because I'm saying how much time and cross-sectional area. So gases and liquids have two measurements of flow. Gases and liquids have two measurements of flow. So you could have, so let's come over here. You could have a constant rate of flow, but a change in the velocity of flow. So let's say you were flowing and you went into a pipe. So let's say you were flowing and you went into a pipe that had a large cross-sectional area. You went into a pipe that had a large cross-sectional area. Let's see if I can find something real quick here. So let's say I'm going through, put this up here, this pipe here. Check this out. I'm going through this pipe. And I'm saying I come out of this pipe with a rate of flow. And I enter this pipe with a rate of flow. Same rate of flow. Let's say 25 milliliters per minute here. Go through 25 milliliters per minute. So uniform. What comes out goes this way. What comes out. But the cross-sectional area of this here is much larger than this. So even though I would have a uniform rate of flow all through here, milliliters per minute, because I'm dividing by a cross-sectional area, the velocity of flow would slow down here because there's more cross-sectional area. See, the velocity of flow would slow down here because even if I did 25 milliliters per minute, but when I got to this area here, because the cross-sectional area is larger, the velocity of flow. So you could have the same rate of flow, as we'll see. See, in cardiac output, which we learned in the heart, we said about 5 liters per minute. What's the 5 liters a minute? That's rate of flow. You have to have 5 liters per minute coming out of the heart itself, let's say into the aorta, and you have to have 5 liters coming back. Otherwise, it would back up someplace. But you could change the velocity of flow along the way. Key issue is you read the book and think about what I'm saying. So rate of flow would be example cardiac output, but velocity of flow can change, and we'll see that it's going to change in the capillaries, which are the exchange vessels. Okay? All right. So I want you to think on this. These are situations I need for you to really think on. Okay? So now we're going to go a little further. All right. Now we're coming to resistance. Okay, the holdback force. Resistance, a force of impedance, holding back. Now resistance equals to 8 nu L over pi r to the fourth. We're going to talk about resistors in series, resistors in parallel. But this is the formula. Okay, so let's go a little further. The formula was saying that resistance equal to 8 nu L over pi r to the fourth. All right. Nu, this Greek word, is the viscosity of the gas or liquid. So think about that. That's in the numerator. You've all had to pass math. Since it's in the numerator, an increased viscosity, the thicker something is, the more resistance. See, 8 is a constant, nothing to say about it. L is the length of the pipe you're going through, the length of the pipe. The longer the length of the pipe, the more scraping on the side of the pipe. The more scraping on the side of the pipe. That means the more resistance. See, it's in the numerator. Pi is pi. You know that from geometry in 5th grade, 6th grade. Ara is the radius of the pipe. Check that out. Ara is the radius of the pipe, but it's raised to the 4th power. That's the only thing in this formula raised to the 4th power. That means the diameter of the pipe, i.e. radius, which is half, the radius of the pipe has the most to do with resistance because it's raised to the 4th, which is tantamount to vasodilation and vasoconstriction. Now that's in the denominator. So the wider the pipe, this number gets bigger, the less the resistance is in the denominator. The narrower the pipe, the vasoconstriction, the resistance goes up because the number gets smaller. So this vasodilation, vasoconstriction significantly affects resistance. Significantly affects resistance. Now, adding up resistances. This is the summation sign. If resistors are in series, now let's go to another picture here. If resistors are in series, that means going from this pipe to that pipe. That's in series. Then you would add up the resistances as R1, R2, R3. Now each R equals to 8 nu L over pi to the 4th. So you would add up R1, R2, R3. See, that's a series from here to there, taking that branch. Or from here to here, up to there. Because this is smaller than that. So this would have a resistance and that would have a resistance. But if I look at parallel, now see, here's the parallel. These are pipes and they're in parallel. Then the resistance, total resistance is less because it's the reciprocal value. 1 over R1, 1 over R2. So this arrangement gives less total resistance than the series. Resistors in parallel give less total resistance than those in series, which means less holdback, less holdback. Now I want you to think of that as we apply this when we get back to blood vessels. Okay, so that's adding up the resistances. Okay, I'm going to end this right here and we're going to pick this up on this slide here.